Alright, so we're going to look at the motion of a projectile on, say, the Earth, okay, so a rotating sphere like this, and we're going to be located at some position on the Earth's surface out here at some co-latitude of theta, and just to keep things simpler, we're not going to be launching the projectile with any from one location to another on the Earth. We're just going to be sticking mainly in the z direction, so straight up and down with respect to the Earth's surface at this point. So first we're going to just look at dropping the particle right from a certain height straight down towards the center of the Earth, and we're going to just see how much the Coriolis force would deflect it. Alright, and then we're going to compare that to the case where we take that particle and launch it upwards from the ground up to the same height where we had originally dropped it from, and then let it fall back down to the Earth. So we'll see how these two cases are different. Alright, so first of all, we need our equations of motion. Alright, so at this point here, there's going to be, we're just looking at the Coriolis force, alright, and that's a minus 2m omega cross with the velocity of our particle. Okay, and so when we look at the velocity of our particle, we are making the approximation that it is only in the z direction, right? Because it's going to be moving much further, faster in the z direction than it would be by some small shift in x or y. All right, you know, if you drop an apple here wherever you are on the Earth, you look at it and it looks like it's falling straight down. So that's kind of the approximation that we're going to start with, and then we'll find how much it would actually be deflected. Okay, so just knowing that this v is mainly going to be in the z direction, all right, we can then take this cross product. All right, so we'll have a minus 2m, the magnitude omega, the magnitude of v. I'm going to put a little subscript z on this. All right, and then sine of theta, so the angle between this omega and this z. All right, and by the right hand rule, we're doing omega cross v, so we're going from this way to this way. That would point our resultant vector into the page, so in the x hat direction, like this. All right, I guess I should real quick. So these x, y, and z are defined here near the Earth's surface at this point. So y would be pointing towards the north, and x would be pointing towards the east. All right, and our sphere is rotating towards the east, just like the Earth is. All right, so intuitively, if we were to take a particle here and drop it down to the center of the Earth, the Coriolis force, we would expect it to move to the east, right? So in that case, this v would be negative because we're going in the minus z direction, and that will cancel with this minus sign, and we'll get force force in the x-hat direction. So another way to, a quick way to remember this is just that we are, when you come in from the height h down to the Earth's surface, you're moving actually closer from up here, wherever this h is, down to the surface. You're moving closer to this axis of rotation. And so just like the skater on ice, you know, spinning and bringing her arms in, you're going to rotate faster around this point. So as the particle moves downward, moving closer to this axis of rotation, it will move around this axis of rotation, like conservation of angular momentum. It will move faster than the Earth itself will. So it's going to get ahead of the Earth and move to the east. All right, so let's go ahead and write our equations of motion. So we have this force that's in the x direction, okay, and then of course we'll also have gravity in the z direction. So let's write these out. So F equals ma. So here's the ma, and we'll write out the F. So minus 2 m omega v z sine of theta. Okay, and y, let's do y. We don't have any forces in the y direction. And our acceleration in the z direction is just g. So the force is just the weight. So minus mg. All right. So what we're going to do is integrate this equation first. So then we get z dot instead of z double dot. So the velocity in z. Once we know that, we can plug that into this equation and then integrate this equation a couple of times in order to get the final displacement in the x direction. Okay, so before we start this, let's look a little bit just at the projectile motion. That equation, our position, we would expect to be a minus 1/2 gt squared plus whatever initial velocity multiplied by t plus whatever initial position we're at. So there's just a couple of things that we'll want to get from this that we may need later. All right. So again, the two cases we're looking at is, let me finally just define a height h here for convenience. So if this little mark here represents the height h. All right. So two things that we will need. One is, in free fall, how long would it take to fall from height h down to the ground? So we just want to know what that time is, and also how fast is it going when it gets there. Okay, so first of all, using this equation, we would get a 0 here, and we're dropping it, so we get a 0 here for v naught. Let me go ahead and write those in. So and then here our initial position is h. All right, so no initial velocity, but an initial position of h. All right, so if we bring this over, we get a 1/2 gt squared equals h. All right, which gives us so we have a 2h and then divide by g, and then we take the square root. Okay, so this is going to be helpful. All right. The other question is, this is getting a little bit jumbled. But how fast is it going when it reaches the ground? All right, so if we take this equation back a step and we just say the v equals minus gt plus v naught. Okay, the v naught is going to be 0. All right, this is the dropping case, and so we just plug in this t. So we're just multiplying by g to get the final velocity. I'm just going to look at the magnitude of this. Okay, so multiplying by g, we just get 2gh. All right, so this magnitude will also be important. Why will it be important? Just because when we do our second case, where we're launching the particle up from the surface of the Earth, we want it to get exactly up to height h, where we're dropping it from, so that way we can compare the two more easily. So, so this is this is important just because this is the speed with which we need to launch it in the z direction to reach exactly the height h that we dropped it from before. All right. Another quick thing. So this is how long it takes to fall from height h down to the ground. When we're launching it, the total time it will take is 2 times that. So the motion is symmetric, right? So it will go up in this same amount of time, as long as we're launching it with this speed, and then it will take that same amount of time to come back down. So, all right, we'll just get into this. So our first case is drop from z equals h. So we're just going to go ahead and integrate this equation. We're going to be just setting the constants of integration to 0 or whatever they are as we go. All right, so looking at this equation, let me just divide by the mass. We have z double dot equals minus g. All right, integrating this, we will have z dot equals minus g t plus the initial velocity in the z direction. All right, which in this case is 0 because we're just dropping it. All right, in the next case it won't be 0. All right, so now we have our z dot, all right, which is equal to vz. So we're going to plug that into this equation now. And again, I'll divide by the mass. So we have x double dot from up here equals minus 2 divided by the mass omega vz sine of theta. All right, so now we can plug this in. Our minus sign goes away. We get a 2 omega g sine of theta, and also this factor of t. All right, so now we're going to integrate this equation. So we get the t is going to be squared, and then we divide by half, so the 2 is going to go away. Omega g sine of theta, and then t squared. Okay, so and then we need our initial velocity in the x direction. All right, which is 0. We're just dropping it straight down, so that's 0 anyway. Okay, finally, we integrate this one more time. We have now omega g sine theta. Okay, now we're going t cubed and dividing by 3. And now we add on our constant of integration. with the initial conditions. All right, so now that's the initial x position, which is also 0. Okay, so that's also 0. All right. Okay, so here we have our final, our x position after a specified time. All right, and so we now will plug in this time right here. Okay. So we will have a 2h over g multiplied by the square root of 2h over g. So this is just to the 3/2 power. So it's already under the square root, and then we're cubing it. So let's just write this a little bit nicer. These g's will divide out, and we'll have a factor of 2/3 in the front. Okay, we also have an h from this, and this 2h over g, and then a sine of theta. All right, I think I got all those pieces. Okay, so now now we see that this is positive, right? Positive x means it is going to the east, just like we predicted. Now we will launch it back up, starting at x equals 0 again. Okay, launch from the origin with a velocity of 2gh under square root in the z direction. Okay, so we're launching it straight up from the Earth's surface, and then we're going to let it fall all the way back down. All right, then we'll see what the net displacement is for x. So we'll just go through this process again. So starting here, we have z double dot equals minus g. Solving for our velocity, we get minus gt. So integrating plus plus we'll get our initial we do have an initial velocity in the z direction this time, and it's 2gh under a square root like this. All right, so now we'll move on to our x equation. So let's go ahead and divide by the mass. So we have a minus 2 omega sine theta, and then this factor from right here, the v sub z. Like this. Okay, now we will go ahead and integrate this. Okay, and we could put another constant of integration out here, but our initial x velocity is 0. we're launching it straight up, not at some direction along the x-axis. Okay, so integrating one more time. And then our constant of integration out here is again 0 because we're launching it from x equals 0. All right. So now what we need to do is just plug in our t. And I hope there's enough room here. Okay, so when we put in the t cubed, we'll just get what we got before. So this cubed, so 2h over g to the 3/2 power, or a 2h over g multiplied by 2h over g under a square root. Okay, and then here t is just squared, so we just get 2h over g. And I forgot something important, which was we're not using this time, right? We're using 2 times this time. So, right, because it takes twice as long to go all the way back up and all the way back down. So what I need to do is multiply this term right here by 2 cubed, so 8. Put an 8 in there, and a 2 squared on this one, so a 4. Okay. Looks like we're on to a new page. Let's see if we can simplify some of this down. I'm going to bring out a 2h over g under a square root. See how that does for us. So now we have, so we'll have a minus 8 over 3, and the g's are dividing out, and we just have an h, so there's our first term, plus this 4 and this 2 will just give us a 2, and then we have a square root of a 2gh, and I already took a half of this, or I took 1 square root of this out here, so what's left is 2hg, which is also under a square root, so 2h over g. Okay, so the 2, we have a 2 squared in there, these 2 2's, so that's going to come out as a 2, so we get a 4. This g is going to cancel out, and then we have an h squared as well, so we get an h out. Alright, so let's go ahead and look at this. Putting this over the common denominator, we'll have a 12 over 3 minus an 8 over 3, so we're left with just a 4 over 3. And multiplied by 2, that's a minus 8 over 3. And then, oh yeah, we have this h as well. Okay, so here's our answer for the case when we're launching it from the bottom. So we can compare that to our previous answer. So we have the omega, we have the h, we have the sine, we have this factor of 2h over g under a square root, and the big story here is this extra. So we have a minus 8 over 3 rather than 2 over 3. So this one is actually 4 times as large, and it is in the westward direction. So it's coming out at us this way. All right. So why is it so much larger, and why is it in the opposite direction? Well, that just tells us that the Coriolis force is having a much larger effect in the part of the motion where we're throwing it upwards. Why does it have that much larger effect? It's because the Coriolis force depends on the velocity. And so when we give it an initial velocity, all right, rather than starting at 0, we have much more time and stronger, right? It starts at a strong, or at a finite velocity, or at a significant velocity. The Coriolis force starts acting immediately at full strength, and that results in an acceleration in coming out of the page, which starts moving the particle immediately, and that has time to act all the way up, and then it finally starts getting counteracted. You know, up here we're at velocity 0, so we don't have Coriolis force, and then when we come down, then it finally starts getting counteracted. So the Coriolis force has had much longer time to work in the westward direction than in the eastward direction. So that's a quick and dirty explanation of why this displacement in the westward direction is so much larger than this one, and of course in the opposite direction. So real quick, maybe we can make this a little bit more quantitative. So if we look at launching, so we're launching from the bottom, and we want to know what is our velocity here in the x direction when we get to the top. Okay, so if we carry out that calculation, we get a minus 2 omega sine of theta multiplied by h. Okay, so that's just plugging in our the t, like 2h over g under square root. That's just plugging that into this equation. And so this is how fast to the west it's moving by the time it reaches the top. All right. Then if we look at our that dropping it from height h, so we know based on our initial velocity when we launched it up that it will reach a height h. So when we were dropping it from height h, we set this the initial velocity to 0. But I mean, and this is in the x direction, by the way. We set that to 0, but if we're launching it up from the ground, then we need to set that to the velocity we found from before. So this would be a minus 2 omega sine theta multiplied by h that we got from plugging the t in to this equation. All right. If we reset the clock and then ask at what t does it stop moving towards the west, the answer that we get, and this might be obvious to some people just based on the symmetry of the problem, the answer that we get is this 2h over g. So that just means that right when we launch it from the ground, it will immediately start moving towards the west with it'll accelerate towards the west, right? And it will continue accelerating towards the west all the way up here to the top. So, but although that acceleration slows down, right? So it's moving towards the west, and it's speeding up as it goes all the way up out here. All right, and so when it reaches the top, it's still moving towards the west, and it also moves towards the west all the way back down to the Earth, where it finally, once it reaches the surface of the Earth, that's finally when the centrifugal force in the east direction is able to counteract not the position, but just the velocity towards the west. So when we throw it up from the surface of the Earth, all the way up and all the way down, all the way to the point where it hits the Earth again, it's moving in the west direction that entire trip. So of course we're going to get a final displacement that's to the west, and obviously it's going to be larger than what we got just dropping it. So anyway, interesting stuff.